Alright, so we'll start with the definition of a factor. A factor is a number that divides evenly into another number. So an example of this is 2 and 3. They're factors of 6 because 2 times 3 is equal to 6. And so for prime factorization, we also need to know the meaning of a prime number and a composite number. A prime number is a whole number that is greater than 1 and has exactly 2 whole numbers which are factors of it. So for example, it would be 1 in itself. So a prime number is 5. 5 only has factors that are 1 and 5. And there's no other ones. Do you have a question?
Isn't 3 a prime number?
Yeah, 3 is a prime number as well. There's multiple prime numbers. And then we have composite numbers, which are the complete opposite of a prime number, and they have more than one set of factors. So for prime factorization, the end of your prime factorization, the solution, should be a set of prime numbers that multiply to equal the number that you are factorizing. So to show an example of this, I will do the prime factorization of 630, and then you can try an example. So if I have 630, I'm going to use a factor tree to factor this. So what are 2 factors that I could use for 630? Go ahead.
3 and 210.
And 3 and 210?
Yeah.
Yep. So once I do this, I already know that 3 is a prime number, so I'm not going to factorize 3 any further. But 210 isn't a prime number. So I'm going to factorize 210. So what are 2 factors I could use for 210? Go ahead.
70 and 3.
So 70 and 3. And 3 is a prime number, so I'm going to leave that be, and I'm going to continue with 70. So I'm going to ask, what are the factors of 70?
7 and 10.
Yep. And this is a good example because 7 is also prime. So you're trying to use one prime number and one composite number so that you don't have to break down 2 numbers at a time. And then for 10, I could just use 2 and 5. So the prime factorization of 630 would be 3 times 3 times 7 times 2 times 5. So it's all the prime numbers listed out, and just to check your answer, make sure that all the numbers that you've listed actually multiply to 630 because you might miss a digit in the middle. So try the prime factorization of 32 on your scrap papers real quick, and let me know how that goes. And get comfortable to find the prime factorization of 32. Are there any questions? Alright, so we'll move on to monomials. A monomial is a number, variable, or a product of a number, and one or more variables raised to a power. So an example is 7x, 25mn squared, and 24y cubed and z squared. These are just a few examples. Just keep in mind, when you have 7x, x is to the power of 1, so it also has a power. So when you're factoring a monomial, you're going to look for the prime factorization of the numbers, and then you're going to factorize the variables. So, for example, in 24, so I'll look at this example. I'm going to find the prime factorization of 24 using my factor tree. So when I find the prime factorization of 24, I get 3 times 2 times 2 times 2, and then after I write that out, I'm going to write the factorization of y cubed. So y cubed is y multiplied 3 times. So I'm going to write that out 3 times, and then z squared is z multiplied 2 times. And we looked at these in the first lesson, so I'm gonna write out C 2 times, and this would be my factorization for a monomial. This is the most complex it will get in the homework worksheets. But when you are solving equations, you're going to use these rules, so it's very helpful to know them. So moving on, since we covered our factors and prime factorization, we're going to be looking at GCF, which stands for greatest common factor. So a common factor is when you list out the factors of two numbers and they have the same factors. So for example, if I have the factors of 6, which are 1, 2, 3, and 6, and I have the factors of 9, which are 1, 3, and 9, my common factors are 1 and 3, because both of these numbers have those two digits as factors. So the greatest common factor is, as its name goes, it's the greatest number of the it's the greatest common factor. So it would be the greatest digit in all of the factors that are common. So I find it helpful to circle the common factors and then just go down the list and see which one's the greatest of them all. So the GCF of this these two digits is 3. Does that make sense to everyone? Alright. So that is all there is to GCF, but then there is relatively prime. Relatively prime is when two digits have only one common factor, which is 1. So 3 and 5, for example, the factors of 5 are 1 and 5, and the factors of 3 are 1 and 3. So this is relatively prime because both of them just have 1 as their common factor. And this is just meaning that only prime numbers can have relatively prime factors, because if I take 5 and also the factors of 6, the only common factors I have are 1. So these two are also relatively prime. Does relatively prime make sense as well? Alright. So let's look at the least common multiple. So the least common multiple, to understand this, we first need to look at the definition of a multiple. So a multiple of a whole number is the product of the number and any non-zero whole number. So for example, the multiples of 6 would be 6, 12, and then so on. So they're just the tables of multiplication, basically. And a common multiple is when two numbers have multiples in common. So for example, if I'm listing the multiples of 3 and 2, it would look like this for 4 digits of 3, and then for 2, it would look something like this. So my common multiples between 3 and 2, we have 6, and we also have 12. So my lowest common denominator, lowest common multiple mentioned here would be the lowest of all the common multiples. So all my multiples, I'm going to circle them. So 6 is a common multiple, and 12 is a common multiple, but 6 is the lowest of them all. So 6 is going to be the lowest common multiple of these number lists. So LCM and GCF are found in relatively the same way. You list out the factors or multiples, and then just look through the list of common digits and justify between the greatest and lowest. So LCM helps with LCD. LCD stands for least common denominator. And to find least common denominator, you just follow the process of lowest common multiples, and that is basically what a lowest common denominator is, except it's in a fraction. So for example, if I had 1/3 and 1/2, I would find my lowest common denominator. Using these lists, I would find that 3 is my lowest common multiple. So I would want my fractions to have the denominator of 6. To do this, I want to find the digit that makes 2 into 6. So I would do 6 divided by 2, which is equal to 3. So the denominator is 3. And there has to be a digit on top, which is going to equal out the 3. So does anyone have an idea of what that digit could be? Alright, so that digit would be 3 because a number divided by itself is always 1, and you cannot multiply any number with any digit except for 1 because that would be an imbalance. You would be changing the value completely if you aren't multiplying by 1. So this would help me find my lowest common denominator. It would be 3/6. And I would follow the same process for 1/3. I would multiply it by 2 by 2 because 2 by 2 is equal to 1. And also, it would help me find my common denominator of 6. So it would become 2 by 6. And now these fractions have the same denominator and I can use them for addition or subtraction easily. So just to try a few problems, try finding the lowest common denominator of 5/6 and 7/9 on your piece of scrap paper. Alright, does anyone have any questions on this question? Alright, so we'll move on to the rules of exponents. So I don't know if we remember, but we went over the basics of exponents during the first session. Would anyone like a review of those? Alright, so let's dive into the rules of exponents then, if we all remember the gist of exponents. So there are 3 rules there that we're going to cover right now, which are going to be the product of powers rule, the quotient of powers rule, and also we're going to be looking at the 0 and negative exponents. So the product of powers rule is something that looks similar to this. So a to the power m times a to the power n. So you can see it more clearly. I'll write it out again. And these two, when you multiply them, you aren't going to be multiplying the bases as you might be thinking. So just to brush up, a is the base and m and n are the exponents. So when I multiply these two, my m and n are going to be added. So it would become m plus n. And for quotients, it would look very similar. It would be a to the power m divided by a to the power n. And this would equal to m minus n, and the exponent, and a is always going to remain the same. So this is what the rule looks like. And just to see it in perspective with numbers, it's going to be used to solve equations. So if I have 2 to the power 2 times 2 to the power 3, what is that going to equal? Go ahead.
2 to the power 5.
Yes, because they're going to be added. It's very easy to think of these exponents as multiplying, which in this case they will not be multiplying. But there is a case they will be multiplying in, which is when you have parentheses. So if I have a to the power n in parentheses, and outside I have a to the power n to the power m, this will be multiplying, and the reason is because you are going to expand the parentheses, and so it will look like a to the power n m. So to see this in perspective, because this can get a bit confusing, if I have 2 to the power 2 times to the power 3, what would that equal? Go ahead.
2 to the power 6.
Yep, so just remember the key differences between when you're multiplying and when they're in parentheses. And also, if you're dividing, it's going to work just like multiplication. Just remember that subtraction is the opposite of addition, and division is the opposite of multiplication. I would like to remember a table which looks similar to this. This is supposed to be division. And the reason is because it relates all of my different operations. So this shows that addition and multiplication go together as they do in this example, and it shows that subtraction and division go together as in quotients of powers. So do the rules of exponents make sense to everyone?
Mm-hmm.
Alright, so let's try a quick example so that if you have any questions you can ask. Okay. And then we'll try quotients question as well. Alright, are we all set to move on?
Mm-hmm.
Alright, so this, for the first question, this will equal 2 to the power 16 because it is in parentheses. You'll multiply the 8 times 2. For the bottom, this is going to lead us into our next topic, negative and zero exponents, because what's going to happen is your base is going to remain the same, but it's going to become 2 minus 2. Now, that is a zero exponent. That means it's 3 to the power 0. This doesn't equal 0 because it means you're multiplying 0 times, and so it's equal to 1. So this is harder to remember, but when anything is power to, like when anything to the power 0 is equal to 1. So if I had 2 to the power 0, 5 to the power 0, even if I had 1,000,000 to the power 0, it's always 1. And so now we can look at the negative exponents. Negative exponents form a fraction. So if I have 2 to the power negative half, into fractions yet actually. So if I had a negative 1, anything to the power 1 is equal to itself because that means you're multiplying it one time. And when you multiply anything one time, it's going to equal itself. But now there's a negative. So what do I do with that? Well, if there's a negative, to make it positive, you can always move the digit into the denominator. So this would be equal to 1 by 2 to the power 1. And that would make my exponent positive if I move it down into the denominator. And this is equal to a half. But then what do I do if there is a negative exponent in the denominator? So if I had 1 by 2 to the negative 1, my exponent would be positive if I just shift my digit to the opposite side, which would be my numerator. And so now I have 2 to the power 1 by 1, but my exponent is positive, so that's my goal. And then 2 to the power 1 is equal to 2. So whenever you have a negative exponent, just flip it side, and it will become positive. Any questions? All right. And so there are also exponents which are not whole numbers. For example, if I had 2 to the power half, this is something that you're going to cover in Algebra 1, but we can go over it since we're covering the rules of exponents. If you have fractions, does anyone have an idea of what you can try to do to get rid of the fraction? Alright, so if you have a fraction, that basically means it is going to be a radical. So since I have my 2 in the denominator, that is a square root. And my base is 2, so my 2 will just pop in. The square root of 2 is not a perfect square, so we don't need to worry about it right now. But if I did have a 4 here, and if I had the square root of 4, it would be 2. And the reason is because it's the opposite of exponents. So 2 to the power of 2 is equal to 4. So if I have the square root of 4, it's basically a 2 here, which means it's x squared is equal to 4. Sorry, I wrote that the opposite way. It's 2 to the x is equal to 4. So I'm basically trying to find, what to the power of 2 is equal to 4, which is 2. So the square root of 4 is equal to 2. Does that make sense?
Yes.
Alright, sounds good. So now we're going to be looking at something very fun. It's scientific notation. This will help you solve multiple word problems that have bigger digits. And it will also hopefully help you understand the calculator a bit better. Sometimes, I don't know if you've experienced this already, but when you enter numbers into the calculator, you might see a digit, and then you might see E, and then more digits continued, and that is going to be showing scientific notation. So we'll take a look at what scientific notation exactly is. It is anything that is written in a similar format to this. And in this circumstance, C is always less than 1, but it is always greater than 0. The circumstance that you use scientific notation is if you have digits that are humongous or very small. So if you would like an example of a word problem that you may see, I can read one out. So this is related to anatomy and the eyes. So the eye has a layer in the eyeball that contains rods and cones. Rods and cones are cells and absorb light and change it to electrical signals that are sent to the brain. The human retina is about 0.00012 meters thick and contains about 120 billion rods and about 6 million cones. So if you are solving a word problem similar to this, it's hard to put into perspective if you are just talking about these very large and small numbers. So scientific notation will help you tackle those type of problems. So eventually after this lesson, you'll be able to solve similar questions and put circumstances like this into perspective. So to write in scientific notation, we'll take one of the numbers that were mentioned in the problem that we looked at. So it was 0.00012. And so my C needs to be something that is between 1 and 10. I wrote the numbers wrong. So it needs to be between 1 and 10. And if I'm looking at this number, my goal is to actually move the decimal in order to get something between 1 and 10. So what number would I eventually result in after I move the decimals? Go ahead.
12.
12 is very close, but it is greater than 10. So we're gonna take 1.2. That's actually a very good guess for C. But C in this circumstance will be equal to 1.2. So now I ended up with 1.2 times 10 to the power n. But I don't know what n is yet. N is the number of times you jump your decimal. So, in this circumstance, I moved it 1, 2, 3, 4 times because I want the decimal to come up right there. And so 1, 2, 3, 1, 2, 3, 4 times. So n would be equal to 4, and it'll be 1.2 times 10 to the power 4. 10 to the power of anything is basically just implying your zeros or decimal movement, but I did move it to the right, and anytime I move this, move my decimal to the right, my exponent on the 10 will be negative, and anytime I move my decimal to the left, it'll be positive. I think you had a question.
Oh, no, I was just saying that it's supposed to be negative.
Oh yeah, thank you for that. Yeah, so that's an important thing to remember that a lot of people forget, including myself sometimes. But a good way to remember is that if you're making a decimal bigger, when you're moving your decimal over to make it 1.2, for example, from such a small number, it's usually always going to be negative, and whenever you're making a bigger number smaller for scientific notation, it'll be a positive decimal. Alright, so does scientific notation make sense? I know it can be a lot to grasp at first, but it'll eventually you'll get comfortable with it. Any questions? Alright,